Okay, hello Nidir. Uh, I just thought we'll just make a quick video for Kirchoff laws. It's not a very hard topic. I don't know if you have done this already in school, but we'll just cover it very quickly. And if possible, we might also go to resistance and resistivity. But let's see. I have not seen the chapter yet. So let's see. So we'll start with Kirchoff laws. So there are basically only two, three things that we're going to talk about. The first, yes, two laws, both of which are the basis of modern, like just electronics, right? So it's the current law and the voltage law. So as I was saying, this is the basis of just electrical engineering. In a way, a lot of like the circuits thing is understood through these two laws. So very, very important. So it cannot be understood how important that everyone knows about them, and it's just critical. Okay, so the first law, I will state both those laws first. It just states that the amount of current coming in, right, is the amount of current going out. So if there is I1 and I2 going out on every node in the circuit, whatever is the current coming in is the current going out. So I is the current coming in, and I1 and I2 are the current going out. So then this is the out part, and this is the in part. So it happens to be only one of the current is coming in here, which let's call it I3 here for example. So then it is I3. If then say there is more wires connected to this, uh, then this will also be, maybe this is I4, and this will become I4 also here because I4 is coming in. So this is the first law. The second law states that the second law is a little more complicated. It states that whenever you have, so this was the first was about a node. This one is about a loop. So you need a loop of things around. So you have components along a loop, right? So so there will be some components that give energy and some components that take energy, right? So and the Kirchhoff's second law states that the the components that are giving energy must be countered by exactly the components that are taking away energy. Your book states this as EMF components, and this is and this is potential difference PD or potential eters. So if you remember from last time, you can refer to the last videos also. So you talked about how if you have a battery and say you have a resistor, then if this battery has an EMF equal to E, that means it is given up energy of E. And then if you fall across, and if that same resistor goes across, if the charge goes around the resistor, it loses energy. So we define potential difference or voltage as the amount of energy lost that was equal to I times R. If there is a current of I flowing through this, then this was equal to, uh, so in this case, so the energy lost is equal to I times R, right? So this is the energy lost. Now we say that this is the energy lost, and what is the energy gained is E. Like energy given is E. So the left side of the equation is E, and the right side of the equation is I times R. So they must be same in the lower circuit. In the bigger circuit, let's discuss it there also. So maybe there is one battery component, right? It gives energy. Maybe there is a resistor component that eats up energy. Maybe there is another battery component, uh, which is in the opposite direction, right? So if you think about it, the good work that this E1 does, this E2 does the opposite of that. So it's effectively E1 minus E2, right? The amount of energy given it. Something like that. You might have more resistors. There might be another resistor, then another resistor, R1, R2, and R4, 3, right? Maybe there may be another current source. Just take a moment to pause the video and see that the amount of work done by E3, is it helping E1 or is it opposing E1? So let's see. So if we think about it, then if when this when so when the circuit, when the charge goes from here to here, it gains energy from negative to positive. So the charge comes out from here with a lot of energy, but then when it goes from here to here, it is again more accelerated. So E3 helps E1. But on the other hand, if you see that the same charge that loops around in a in anti-clockwise manner, so once it goes across this battery, it loses energy. You see, it enters at the positive plate, so it is opposed. It is met with the resistance, right? So so you need to understand the convention, and maybe at the end, maybe we have another resistor right here at the end, which is R3, right? So in this case, how do we write Kirchhoff's voltage law? It is so we write all the components that give energy. So E1 gives energy, right? If we go around the loop in an anti-clockwise way, so you need to decide the direction first too. So one of the very important component is direction. So you decide to go anti-clockwise like this. And this is only a this. So you see anti-clockwise, right? So E1 gives energy, right? What and then E3 gives energy, and then E2 takes away energy. So this is all the giver. So what eats up the component? So whatever this current I that's flowing through this loop, this I times R3 eats up. Oh, the two R3s. Let's fix that. Let's make this R4. Okay. So R4 eats up, and R2 eats up, and R1 eats. All the resistors always eat up. Then this becomes a voltage law in this situation, right? With the current flowing in an anti-clockwise way. So again, if you selected the original direction as opposite, then E1 would eat up energy. Like now we are going clockwise. We are going like this, right? Now our direction of current is like this, which is opposite to the earlier one. So E1 eats up energy, right? Now E2 helps the electrons, and then finally uh, E3 also eats up energy, and that is equal to I times all the thing that actually lessen the energy. So 1, 2, 3, and 4, right? All the four. So now if you compare these two equations, you will see that the right hand side is exactly same, right? While the left hand side, all the signs are reversed. That is because the current direction is reversed. So if you replace I with minus I here, you will get the equation above. So it's the same thing. So here the I is clockwise, and in this case I is anti-clockwise. So this is very important to understand these little things. Okay, so if you understand this, then actually the chapter is frankly over. But we are going to carry through a couple of examples that just it just drills in nicely, right? So let's try to see some examples. You can definitely go through the book, it will help you. So let's try to do a simple example first, right? Let's try to do something like this. So there's a 6 volt. So let's see what they're trying to do. So you have a few components that are giving and taking away energy. It seems like this 6 component, if you go in the mentioned direction here in the loop, in the red direction, so this 6 will give energy, right? It makes sense. And but then if you think about this, then this opposes that 6. So your giver total it is 4 volts, and is eaten up, which that 4 volts is eaten up by these two resistors, right? So if say there is a current I flowing, then this will be eaten up by I times 10 plus I times 30. So and now we know that now we can try to solve this equation, right? So let's see what we are trying to talk about here. So there is one battery source that gives, and then there is one battery source, and let's not write plus 6. Plus does not mean anything. So this is a 6 volt battery source and connected in opposite sense with a 4 volt battery source. We have two resistors, 10 ohms and 30 ohms, and we have to find what is the current in the circuit. Okay, So again, we try to move in a decided direction. So we decide the direction to be anti-clockwise or clockwise. It does not matter. So in this way, when we are moving to the direction is in the same direction as current, that's good. So we write all the current sources, all the EMF sources. So that's plus 6 and minus 2, and that is eaten by I times 10 plus 30, right? So if because I write it in this common way because the current through both of them is same, eh, and then you just try to solve it, right? Let's keep moving. 40 ohms, and this is also 4, so I will be equal to 0.1 ampere, right? So now, just for example's sake, let's try to see what happened. What would have happened if you would have chosen the opposite side of movement? Maybe like like this. So we said that here so let's try to write the Kirchhoff's law for this. So in this way, the 2 is a helper and 6 eater. So this is the net EMF, and this is eaten by I times 10 and I times 30, right? So the total is 40 times I. It will be equal to minus 4, so I will be equal to minus 0.1 ampere. So all that means is the direction of current that we have chosen is opposite to that what we have assumed. So it's opposite in this sense. So which brings us back to, so it is, we can say the current is minus 0.1 clockwise, which is what this tells us, and this one tells us it's 0.1 anti-clockwise, right? And both of them are the same thing. So that's the idea. So you need to understand when to take positive and when to take negative, because this is very important. So this is a basic example. Let's try to look at a couple more, because that's all you have to do in this chapter, because the concepts are really simple. Okay, so let's look at this now. So they're saying that there's a battery here, there's some current flowing out, and then we have to find what is this resistor, right? Okay, so let's look at it. So it's saying that there is a battery of 10 volts, there's a resistor, and then there's another resistor. This resistance is known to be 20 ohms. This resistance we don't know is R, and then we know that there is also a current flowing in this direction of 0.1 ampere, right? So just checking the numbers. Yeah, looks right. Okay, cool. So now let's try to see how, if we can find R. So let's first select the direction of a loop. So direction of loop we are selecting as anti-clockwise, right? As we said that it does not matter except we have to take the signs properly, right? So all the EMF sources that give help this anti-clockwise motion will be 10, and that's all. And all that eats up is zero point 0.1 times 20, that eats up, and then zero point 0.1 times R, right? I times R and I times R. So this will be equal to 2 plus 0 0.1 times R and 10. You should definitely pause and try all of them on your own. Just this is a general thing, right? 1 times R, so R will be equal to 80 ohms, right? Like again, just for exercise sake, this is the final answer. But if you were to take a clockwise loop, what would have happened? So just to, this is like an extra exercise. If you were to take like this, so in that case, your EMF source actually does not help you. It opposes this motion. It does not give you energy. It kind of eats it up. So this is the net EMF. And on the other side, now this will be some, some current. So we know that this will be now minus 0.1, the current, right? And then that will be equal to minus 0.1 times R and minus 0.1 times 20, because the direction of current is opposite to the direction of the loop. I know this is all a little confusing right now, but you'll get through it with enough practice. Simplifying this, minus 10 minus 0.1 R and minus 2, get this over here, minus 8 minus 0.1 times R, and then minus 8 by minus 0.1 is R, and R you get as 80, which is the same thing as the previous one. So when you select the direction of the loop, only the direction of the current you need to take care of. This is the important one. So here we took it as positive and there we took it as negative. Rest everything. So EMFs will also be reversed. So you need to take care of something. But resistances are not reversed. You will see it with practice, definitely. Okay, let's do more questions because all that's all we are going to do. So let's do a more complicated question where there are say two loops, something like this. So this is a more complicated question. So let's look at this. So there is a battery source up top which is giving 6 volts. It's giving some current I, right? We know that that I, because of Kirchhoff's first law, will split into I2 and I3. That is to say I2 plus I3. So in this case, you can see that all the incoming sources are I2 and I1. So I1 plus I2 must be equal to I3, right? Everything that's coming, if you look at the node P, then I1 and I2 are coming in, and I3 is going out, right? Okay, so it's coming, it's giving some current I, and it's also must take that same current I, and then you're adding some current to it from here. And why is this current coming? Because there is another voltage source that's trying to push in more current, right? So it's like this is like an aggregator branch. So two currents are flowing through this, and then they split them back into their own thing. So this 30 is kind of having to deal with both the current flows. Okay. So let's see how we can look at this. So in this, first we select a loop, right? So that's the thing we used to do. So here they have selected the big loop first. So you can select this small loop, and or you can select one big loop. You have to select any two of these three. So they have selected the big one first. So when you're selecting the big loop, this 30 is of no concern. So you start looking at what all is there in this loop. Okay, so this will be discussed later, but they have changed the circuit up a little. They have now added two EMF sources up top instead of a single one. There are a couple more resistors added, and then there is an EMF up at the bottom also. So anyway, so we look at the big loop. So we see that when we go in say an anti-clockwise way, what's helping us and what's not helping us. So this is helping, and what about this one? This is opposing, right? If you think about it from all going towards the big plate, it helps. So this guy helps, this guy helps, and then this guy, because small plate, it opposes. So E1 plus E2 minus E3, so sum of EMFs, right? Okay, now we look at what this net energy that you have is eaten up by whom. So you have I times R, I1 R1 is eaten up by this. I2 R2 is eaten up is given by this. So let's see. So we said that, so let's try to review some theory here, right? So we discussed last chapter that if there is a current I that's flowing through a resistor, you can't see. Okay, if there's a current flowing I flowing through the resistor, then you lose energy, right? Like that's what the voltage difference IR was. So if you're moving in the direction of the current and you go across the resistor, then you lose some energy. This current loses energy. So so last chapter we said that this energy is given by something. It's filled up with energy. Then it does an activity, experiences some resistance. So it loses energy, and then it comes back to the starting end of the battery extremely tired. So this battery again gives it energy. Then it loses it through the resistance, and then it does. But then if you think about it in the other way, it's like running the time in reverse. Then if you start from opposite way, then this had low energy at this point, and then you go up, and then if you go in the other way, then it kind of gains energy, right? Like this is just a, so current direction is not changing. We are just changing a loop direction, so to speak. So we are just looking at things in the other way. So if you think about it from the end of the day, he had low energy. Then we went before the activity that he did, so he had high energy. And then at some point he was just given some energy, and before that he had zero energy, right? So the story kind of reverses. So the same way, right here we have a similar thing where we say that so the thumb rule is move in the direction of current then voltage difference is minus I times R, which is basically losing energy. And if you move opposite to the direction of current, then you gain energy. It's saying that it's like moving back in time in a way. Okay. So if you remember this thumb rule, just commit this to memory. Then we say that okay, so the current is flowing down here, so that means it must lose energy when we are traveling across it. So I1 R1 is lost, but if you look at it from here to here, then we are moving opposite to the direction of current, then I2 R2 is gained. So when we look at all the net energy lost, so it's I1 R1 that's lost, I2 R2 is gained, and then we look at this source and then we continue moving. So this loses energy because we are moving opposite to the direction of current. We here also we are moving opposite to the direction of current. So minus R3 R3, and then we go up. Now we are moving again in the same direction as current. So this is lost. So again, all the signs we said that voltage difference here is minus I1 minus IR because we are losing energy here. But here all we are measuring is the amount of energy lost. So this loses energy, this gains energy, this gains energy, and this loses energy. So this situation is the total energy lost. Now this total energy lost must be same as the total energy given. So hence will make them equal. Again, all of this is complicated, but you will get it as things go on. So let's try to do this one example right here. So let's see. So it's saying that so let's follow what it's trying to say. So it's saying that calculate the current in each of the resistors in 9.11. So let's try to do that. So there's a 6 volts up top, there's a 30, and then there's a 10. So let's try to make this diagram. So 6 volts up top, then there's one resistor here, one resistance here, 30, 10, and then there's a 2 volts in the bottom, and that's it. So and I'm just marking the values. So there's an I2 that flows in the lower circuit we said, and then there's an I1 that flows in the upper circuit, and then which combines into this I3 right here, right? So the first thing, so let's try to write, so as we said, let's try to write Kirchhoff's voltage law in the big loop. So that will be, so let's choose a direction of movement as this dotted line as we have shown, which is anti-clockwise direction. So let's see all this all the voltages that give energy. Plus 6 minus 2. Right? Definitely you should take the time to do it yourself. Pause the video and do it. Okay. So what all voltage sources, EMF sources give energy? 6 gives energy, 2 takes energy in this direction. Your negative to positive plate gives energy, positive to negative plate takes energy, right? Okay. What about the eating part? So this is the net EMF. So let's see. So in this side we have nothing. On the upper side of I1 we have nothing. So if we continue to come down, we have only one resistor, which is this 30 guy. So that's there. So the amount of energy will be 30 times I1, and we are also moving in the direction of I1, right? So if you think about it, we are moving upwards from here, right? And the current is also upwards. So then that means we lose energy, and this is, so we lose energy equal to 30 times I1, right? This is the amount of energy lost. So again, this was the amount of energy given, and this was the amount of energy lost, and those they should be same. So I 30 times I1 was lost and 4 was gained. So we have found the current I1, which was 4 by 30, which will be equal to 0.133 amps, right? So I1 is found. Can we now try to find I2? Sure. So for I2, let's try to choose another loop. So this was in the big loop. We wrote this. Let's try to write one in and another one in a smaller loop. So as we said, there are three choices of loop that you have here. Um, so this is so you have the first loop, which is a smaller loop right here, this one, then another smaller one right here, and then you have one big loop selection, which is the big one right here. So right, so we have already seen what happens when you choose the big one. Let's try to choose the smaller one right here. You can choose any one that you like, any two that you like, but this is fine. Let's choose this one. So if we choose this one and then let's try to choose the motion in this loop also. We say that we maybe will also move, let's say for the sake of this thing, let's select that we'll move opposite direction to the previous one, right? So let's see. So now we're trying to go clockwise. So through the top resistor, now in the small loop, let's see what all are the EMF sources. There is only one source, which is the 2 volt source that ultimately helps. We in the direction of the loop we move from the negative plate to the positive plate. So ultimately you have 2 volts that helps you, right? So this is the amount of energy given. What is the amount of energy lost? So there's only one resistor and that eats up energy. So that will be I3 times 10. So this is the amount of energy that's lost. So from here we can simplify to get 0.1 amp to 0.1 ampere, zero point 0.2 ampere, right? So we have found I3. Can you try to find I2? Yes. So here, so one idea of finding I, like you might think that okay, we might should apply it to the low upper loop, but that will not help you. You can try and check. I would encourage you to try and check. That would again give you that would not give you anything. So I2, for I2 you we must use what we said at the very beginning of the problem, which is Kirchhoff's first law. So we know that I3 is equal to I1 plus I2, right? So from here we can find. So I2 we know I3, we know I1. So we can find I2 from here. So I2 will be I3 minus I1. So I3 was 0.2, this was 0.33. So it will be let's see, 86 milliampere. So now we have all the currents that we need. So we know how much is I1 giving, how much is I2 giving, how much is I3 combined. We know the potential drops across all of them and we are good. Okay. Again, all you require is practice for this chapter. If you don't practice, then it will be a big issue. Okay. So so as a homework, you definitely attempt these two, 6 and 7 for sure. Even if you have done them in school, definitely do them again. Uh, okay. And towards the end, I know that there's one more topic in the middle. I'll just get to that. Also I would recommend you to do all of this. Like I know that there are a lot of sums, but then just spend some time understanding all of them. If you do them, this thing, then they go very fast. Just do everything, like all of these questions. There are not a lot of questions. There are 10 questions, and just skip the theoretical ones. Do whatever are circuit based. Okay, all of this. So because you need to get the signs right, and anything that you have a doubt in, let's discuss that. Okay. So the last topic that we are going to discuss is register combinations. So you know that you know that in the past we have studied that. One second. So resistor combination, right? So we have studied that. So if you have two resistances in series, R1 and R2, then R equivalent is equal to R1 plus R2, which is when you convert this into a single resistor, and they are both same, right? And you also know that if they are in parallel, R1 R2, then you'd say 1 by R equivalent is equal to 1 by R1 plus 1 by R2. So now we're going to look at very briefly how these two happen. So basically it's the same thing. So it's like imagine that there is some current that's flowing into it, I, right? And which should also be the same current that should flow right here, right? I here and then I here. We are looking at the series combination first. Okay, which should also be in this sense is the same current that flows here. If I1 flows here, then I1 must flow out. Right, that must remain the same. So if that remains the same, if you have made the current same, we should also make the voltage same. So whatever current that's voltage drop V that's lost here should be the same as what is lost here, should be the same as what is lost here. Right? So these are the two things that we want. Same voltage drops and same current that's flowing into that terminal. Okay. If that is the case, then let's try to write on the R equivalent side, what is the voltage drop? So voltage drop so our direction of movement is also same as from left to right, like so we'll always choose left to right in this example. So when we move left to right, for the R equivalent side, this voltage drop will be equal to minus IR, we said, right? So minus represents a drop in energy or a loss in energy, and we are losing some energy, it's saying. So minus I1 times R equivalent, right? Now we are being exact. Okay, so let's try to write the same voltage drop for this guy. So it will be some current that will be flowing through this guy, R1. So that's I1 times R1. And then another something will be lost through I1 R2. And of course, all of this is lost, so it is minus, right? So we can equate these two. Sorry, this is not I2, this is I1, right? So I1 R1 is lost through the first guy, and I1 R2 is lost through the second guy. So in total you lose I1 R1 plus I1 R2. So that if you now they because they are the same, you will see that R equivalent will be equal to R1 plus R2. Okay, which is what you always knew. So it's kind of saying that if you have two resistors, you can replace it by a single resistor with value which is double. Okay. So let's try to also do this for the parallel combination. In this case, what we'll try to do is we'll try to equate the currents. So the whatever the current that's flowing in will split into I2 and I3, right? So we will say that we know that I1 equal to I2 and I2 plus I3, right? Uh, so and then let's see. So the voltage drop V that's there. So we can either when we are going from left to right, we can either go from the top one or we can go from the bottom one. So voltage drop should be V across both. So if we go through the top one, then voltage V will be equal to I2 minus I2 R1. Then if you go through the bottom one, it will be minus I3 times R2. Right? Just work them out, similar logic. So here and if we go through this one, and of course in the R equivalent it will be this guy, right? So now let's try to do it. So we have this equation. We can put I2 and I3 from here to here, and then I1 from here to here, like that. So let's try to see. So I1 is equal to V by R equivalent with a minus sign, and then I2 is V by R1 with the minus sign, and then you have another V by R2 with the minus sign. So from there, if you simplify, you will indeed get this value. I know it's all a little complicated. Just pause the video wherever you want. Just try to digest it at your own pace. But the whole crux of the idea you must not forget is if you have two resistors, then you can change them. If you have two resistors in parallel, then you can change them like this. Series or parallel, you know these concepts already. What is important is how you are moving with respect to how the current is flowing. Whether you're gaining energy through these potential difference elements, if you're losing energy. Other thing that's important is this guy that we discussed, the plus sign and the minus sign in the voltage. Another thing that's important is this, the EMF source is what is helping you, what's opposing you. And the last thing that you want to think about is the currents, is the Kirchoff's first law, which is the amount of input, whatever is coming into a node and whatever is going out. So you go through these ideas just once and definitely attempt all of these questions. They should not take more than half an hour, 1 hour. If you get them right, if they took more than that, like just let me know. We'll get these right for you. Hopefully it is an easy chapter, easy breezy, fun chapter, and we can meet next time when you have done these questions. Okay, have a good day. Bye bye.